All right. So I wanted to just again review a little bit about what the test is going to be like and then address some of the questions that you had asked that I cover today in class with regard to review and preparation for the test. And we do have some other things we're going to be talking about as well afterward. It's not entirely separate from what's on the test, but just kind of extending beyond. The only topics we have remaining in this class, so for next week, Tuesday and Thursday, are kind of summary questions anyway, sort of topics that link everything together that are just extensions of what we've been working on all semester anyway. So I don't think that this is something that'll distract you from your goals of studying for the test by any means, but just realize that some of the stuff we're going to talk about aren't specifically things that are going to be tested. The topics outlined for the test, again, is right here in Canvas. And you can see this here. It's not precisely in order of how we covered things, but starts off where we started off after your first Scantron test in class. We finished talking about how to get from rate functions to accumulation, and the last step was getting to exact accumulation functions, exact net accumulation and exact total accumulation, and that's done via integrals. So the integral notation doesn't do anything per se, but just that writing something in an integral form allows us to express in open form what exact accumulation takes place, either in general up through an x or a specific amount between two numeric limits of integration. So then we started reversing the process from there, talking about starting from an accumulation function and getting a rate from it. And we talked about two different methods. The one we stuck with, though, was the sliding interval method of size h. And we went through proving, using that method, several different derivative rules, whether it's just the sum and difference rule or product rule on generic functions, or also we did a little bit with what constant functions, first and second power functions, linear and quadratic. And the rest were basically left kind of up in the air, like, well, this follows the pattern and we'll prove it later. And we've proved several of those later, like we saw the inverse sine function and power function in general for any power, not just first and second power, and pretend that it works for the rest of the powers based on binomials. And we could extend and go on, but that many of those are proven in your book, and I don't want to spend more time proving derivative rules, but just so that you know they aren't just mystery things that I made up. Derivative rules, let's see, for open form rate of change functions. Oh, okay, so this is, sorry, I was just forgetting what this title is. So this is a general process, and then the derivative rules, the shortcuts we did. And then the last few things we talked about were just not in this order. So we talked about, in order, we talked about coordinating accumulation and first and second derivative functions, looking at their graphs, and we'll do a little review of that today as well. And then also optimization and application of derivatives and understanding how that relates to the graphs, why we're looking at derivatives equal to 0, because of what that tells us about the accumulation graph, if its rate of change is 0, or if it's undefined, what that could mean. And then the last topic we talked about was implicit differentiation and its application in related rates, which is just, you know, a slight variation on differentiation that we've done before, finding derivatives or rates of change, but assuming that the symbols that we see are actually entire functions of some variable, whether it's another one we see in the function or just of some understood time variable. But in any case, what I want to do then first today is, let's see, test just in general, because somebody asked, the test is, I'll just type it on here, the test is limited to 60 minutes as opposed to the 50 that it would have been in class. So if you remember, our first test was 50 minutes, even though we had a longer class, we had time to fill out your Scantron and all that beforehand, so it ended up being about 60 anyway, but by the time you're out of there. This one got the extra 10 minutes to make sure your technology is working, get checked in, etc. But you have 60 minutes once you start the test actually, just because I know things happen. Sometimes a page loads slowly or whatever. So it's 60 minutes rather than 50. It's 19 questions, all multiple choice. Now, I'm saying 19 questions. It's not actually 19 separate questions. When you open up the test, you'll see, I think it's 9 or 10 questions, something like that. But you'll have one preface with 2 to 3 follow-up questions in several cases. Some is just one scenario and one question to answer. But like our previous test, sometimes it's one situation and you're asked, like something about the first derivative or something about the second derivative. Maybe you're given a graph and asked to explain several different aspects of the same graph, as opposed to having 19 entirely separate questions. This is 19 questions where several of them are linked together. It's actually about 9 or 10 separate questions. I forget exactly. We redid the test a couple of times to make it more readable. But in any case, it is all multiple choice. There's no free response. There's no fill in the blank. It's just all like drop-down menus or multiple choice radio button sort of answering. Please, prior to the test, please practice to make sure you know how to use the Respondus lockdown browser, have that downloaded. So try the practice test. I think it's called a practice quiz, something like that. It doesn't count in your grade in any way. It doesn't have anything to do with practicing calculus, but it's just about making sure you have the Respondus lockdown browser installed properly on your computer. I don't want you to be trying to download this during your class period, because in addition to the test being 60 minutes, it's not, you can do it during whatever 60 minutes you want. It's only available from 9 a.m. until 10:15 a.m. on this Thursday. So like if you got a little bit hung up at the beginning, that's 75 minutes to take a 60-minute test, of which I really think once you get going, I anticipate it'll probably take you closer to half an hour to answer the questions once you get in. But I don't want you to waste the time during which the test is available downloading the browser and trying to get that set and having a problem with any sort of setting on your computer and pop-ups or whatever it might be. So make sure you try this practice quiz using the Respondus browser. That is, let's see, where is it? Let me go back to here. It is, and I'm not seeing something else on here, but on here, it's at the bottom of module 2. So here's the topics outline I was just in. This is the poll that I asked you to answer. I'm going to go through some of the things people asked about. This is the practice at using the Respondus browser. You can click into it at any point in time. It's a quiz that's password protected and it won't open up unless you're using the Respondus browser. So there's a link inside there that'll help you download it, but also up at the top, testing with the lockdown browser and Respondus monitor. This is up near the top of Canvas. There's an intro with the links to the videos and iMath. This link here has just direct links to here's how you can download it, and here's some videos about taking it. Some of those are included in the, if you link on the practice and download there, it has all these other link outs to do other things. But this should help you get started. This is the quickest way to get to all of that without thinking you're in the middle of taking a quiz. But once you download it, it's set to go after that. When you want to go take the quiz, this practice here, you just have to click on it and you'll be able to see you need to download the browser. So there's another link where you can do it right there. Let's see. This is my view of it, not your view of it. So it won't appear for you right now, but this is, I'll make it available through the 23rd, just in case you want to play with it on Thursday morning. But in any case then, let me put up what I was typing while I was talking, if I can find it. All right, so test is 60 minutes, 19 questions, all multiple choice. It's only available Thursday morning. And please try that practice quiz, because I want to make sure that you know how to use the technology to get in. And again, you can't take the test just whenever you want. It's available during our regular class time on Thursday only. It's limited to 60 minutes. So once you actually press start on the test part of it, it won't let you go past 60 minutes. So it doesn't matter whether you start right at 9 or whatever, it'll cut you off at 60 minutes, but you'll also be cut off at 10:15. So if you don't start until 10, you'll only have 15 minutes. Please don't do that to yourself. Make sure you get started on time. All right, so I'm not gonna be meeting with you on Thursday morning. I'm gonna be monitoring online. There's no like Zoom meeting that you have to link into. It's just go into Canvas and click on the link to get started on your test. Assuming that you have the lockdown browser set, then you'll be set to go. All right, so other things for today. Let's talk about, let me go back to the internet. Not my desktop, what am I looking for? Google Chrome. All right, so let's go back to, so I gotta move some of these out of the way. Reviewing stuff. So I had a request to, how do you decipher between a function increasing or decreasing, its derivative increasing or decreasing, its derivative positive or negative, a second derivative positive or negative, those sorts of things. So in terms of this, I've just pulled up this was a homework question. We're just going to use the graph. So suppose that this graph, as it actually says in the directions, is a function f of x. And I want to answer, oh, sorry, I don't want to use this. I'm going to use the annotation here. There we go. So suppose it was asking about when is f of x positive versus negative. So f of x is greater than 0 if this is a graph of y equals f of x, like it says in the actual directions. F of x is greater than 0 while it's above the x-axis, right? So it's from x2 through that spot. So I'll just color that in red to match my writing that I had before. So here's where f of x is greater than 0. If f of x is less than 0, that's the rest of it. So I won't go on with the color in the rest of this. The rest of it's blue, if you want. So if I wanted to talk about what about f prime of x, I'm going to change colors to something else here. So where is f prime of x greater than 0? Well, f prime of x is greater than 0 when f of x is increasing, right? So this is f of x. It's increasing when left to right. And this, we're talking about functions here. If we have just general relationships that go in circles, there's no sense of increasing versus decreasing except in individual moments, because there's not a whole sense of left to right. But if f of x is increasing as I go left to right, so not at first, but starting around here, then it goes uphill until I reach this top of the hill. And then it decreases and then increases again at the end. So I've got f of x increasing in 2 different intervals here, right? So notice that it changes when I go over the top or bottom of a hill. So the boundaries of these sorts of questions, where it changes from increasing to decreasing, would be at tops or bottoms of hills. Now this graph doesn't have one, but if I did have a graph that went up and then flattened out and then went up again, pretend this is just not going down, just going up again, I would say that it's increasing to the left of this and to the right of that. It's not increasing throughout because there's a spot where it's not increasing. So I also have to be aware of things like that in terms of boundaries. So f of x is increasing between places where the derivative is 0. Which are tops and bottoms of hills, like maxes and mins. Or, although this original graph doesn't have one, if there were some at those flat spots. a pause in the increase or decrease. So where f prime of x is greater than 0 versus less than 0, the boundaries of those intervals are places where it's something other than 0, where the first derivative is 0, or another thing that this graph doesn't have, any places where the derivative is undefined. So those are those critical values, places where the derivative is 0, like tops and bottoms of hills. Derivative is 0, but it's just a flat spot. Derivative is undefined, but the function exists. So the boundaries between when f of x is increasing versus, meaning f prime is greater than 0 versus it being less than 0, are those critical values. So let's see, if we wanted to talk about where the second derivative of f is greater than 0. Oh, and by the way, if it's not positive or 0 or undefined, it's going to be negative. So I've got negative here and negative in that little spot. But I've got too much writing on this graph right now, so I'm going to erase a little bit. And got somebody asking a question here. Let's see. So the question is, would f prime of x be decreasing as it approaches the pause on the cubic looking graph? Yes. So, and that has to do with second derivative, actually. Here, let me erase some of this stuff. But if I can get this. Sorry, I've got too many things on my screen for me to see what's going on here. Yeah, so in terms of this graph and this graph here, in neither case have we talked about whether the first derivative is increasing. That has to do with the second derivative's values. So for instance, and let me pick just a third color here. Let's see. I don't know if this will show up on this graph or not. Yep. So in this graph here, I've got spots where the graph is curved upward in a couple of places. And it's curved downward in between. Where it's curved upward, that's places where the second derivative is greater than 0. Oops, f double prime of x is greater than 0 in those sorts of spots. And it's kind of hard to tell, well, where precisely does it change? Those are those inflection points, and they're really hard to just eyeball, which is why questions related to that had key points like things like these pointed out for you to pick between instead of picking a number, because they're very hard to just guess at, even if there are grid lines. But f double prime, second derivative of f, being greater than 0, this is equivalent, just like f prime is greater than 0, you can also say that's when f of x is increasing. F double prime is greater than 0 is the same as saying the first derivative, f prime, is increasing. When a function is increasing, its derivative is positive, greater than 0. So if f prime is increasing, its derivative, f double prime, is greater than 0. So that's those concave up sections. And again, concave down, the less than 0 is where we've got like the section where x3 and x4 are in this graph. And it's kind of hard to tell precisely where the boundary points would be, but it's either greater than 0, less than 0, or, well, you know, maybe I declare the inflection point, the turnaround point is there. So I've got this curved upward to the right of that spot, curved downward to the left of that spot, and then curved upward. I don't know, maybe here's the dividing point over there. But these two things that I drew on here, just my eyeballing it, are places where the second derivative then would have to equal 0. If it's changing from positive to negative or negative to positive smoothly, then at those two changeover points, it would have a second derivative value of 0. So in this graph on the left here, I've got this is curved downward and this is curved upward. So this is where my second derivative is negative, and this is where my second derivative is positive, which that would also mean here that my first derivative is decreasing That's why its derivative is negative. And this would be where my first derivative is increasing. Its derivative is positive. But notice that again changes here. I've got concave up, which is a positive second derivative, or f prime increasing. So just when you're looking at when something is increasing or decreasing, its derivative should be respectively positive or negative. If I'm talking about whether something is positive or negative, that's about whether its graph is above or below the x-axis if I'm looking at a graph of it. But if I'm not looking at a graph, I have to interpret it some other way. So when I ask, is f prime positive or negative, and I'm not looking at a graph of f prime, I have to interpret that in terms of what does that mean about f? Well, if f prime is positive or negative, that means f, its antiderivative, going backward, would be increasing or decreasing. And similarly, if I'm looking at a graph of, and I don't think we did any look at a graph of a second derivative. That's just hard to interpret back 2 steps. But if I'm looking at a graph of a first derivative, a graph of something called f prime, and I see that it has positive and negative values, I can think about the original graph increasing or decreasing, whether or not I can picture the whole thing. So, all right, let's see. So let's go back to another question that I was asked about review stuff, if I can get this to clear. All right, so let's see. Implicit derivatives was another question I was asked about, just some general implicit derivatives. Here we go. So implicit derivatives, whether it's something like this or it's a related rates question, just involves making sure you're careful about what your derivatives is with respect to. Derivative of y with respect to x when you see y's and x's both. Well, the x parts of that, the x's are the simple regular derivatives like we did before your mastery test, but y, think of that as an entire function that has its own derivative. We don't know what it is. In fact, that's our goal for the question, to figure out what its derivative is. But for instance here, if I have this question, and when you do have these, on your own, feel free to rearrange them and put them in a different order if you like. There's not really any benefit to doing that. You can either do it at the beginning or at the end, unless you have some like terms. But just term by term, taking a derivative of this, of that, of this with respect to x. Now notice this first part, I have x times natural log of y. I've got a linear function multiplied onto a natural log function. So I have to use product rule. So the derivative of x with respect to x times the original natural log of y plus other way around, the original x times the derivative of natural log of y with respect to x. So natural log of, if you want to think of this as natural log of f of x, natural log of a whole function in here, if that's helpful. But the derivative of a whole function, I put 1 over that function. In this case, it's actually called y, and then multiply on, using chain rule, the derivative of that inner function. And the derivative of y as a symbol, I can call it dy dx. So the derivative of just plain y is dy dx. The derivative of a function of y involves chain rule when we're doing derivatives with respect to x. So same thing here, I can think of this as f of x raised to the 5th power. And to take the derivative of a whole function raised to the 5th power, it's 5 times that function raised to the 4th power, and then times the derivative of that inner function, the derivative of y. And then on the right-hand side, there's no expressions with y. I've just got a coefficient and a natural log of x. I'm taking a derivative with respect to x. So 6 times 1 over x, I'm going to write it like that. So at this point, the calculus is done, but the question, we're not done answering it yet because it asks us to find dy dx. And notice that dy dx appears in two places. We've got it here and there, and I need to have something of the form dy dx equals and stuff without dy dx over here, just like regular algebra. If it says solve for y and you have y on both sides of the equal sign, you're not done. If you have y in multiple locations, you're not done. But this is dy dx that we're solving for. It's in two terms, this term and this term. Dy dx is a factor of each of those. Notice that whenever you're doing implicit derivatives, this dy dx is always ever just multiplied on to the first power. It only ever comes from this chain rule. So you're never going to have something like dy dx squared or a square root of dy dx or anything like that. So the technique for solving is going to be pretty similar every time. You're going to have some terms that have a factor of dy dx in them and some that don't. Just separate the terms by whether they do or don't have dy dx. So in this case, I'm going to take this one term and subtract it to move it across the equal sign. Leave these two over here because they both have dy dx. And since they do both have dy dx, and this isn't an Algebra 1 class, I'm going to skip a couple steps and factor it out. So these two terms on the left, I'm leaving them on the left side, factoring out dy dx, and I just kind of combine this x over y because it takes up less space. On the other side, I'm going to have 6 over x minus this term that I've subtracted over there, so natural log of y. And so to solve for dy dx, after we've separated the terms and factored out dy dx, just divide by this factor on the left-hand side to isolate the other factor, the dy dx. So, and it doesn't matter like compound fraction-wise, this is perfectly fine. I'm not trying to make this look pretty, we're just trying to solve for it. Plus 5y to the 4th. And that's done. So we could evaluate this as long as we're given both a value of x and a value of y. You can also see that if y were 0, this would be undefined for a couple of reasons. Natural log of 0 doesn't exist. Also, there's a y in a denominator here. Y isn't a part of the original, y equals 0 isn't a part of the original expressions domain either because of the natural log expression. You could also see that this derivative would be undefined at x equals 0. Same reason, there's a natural log of x. We can't take natural logs of 0, those are undefined. But in any case, here's our expression for this implicit derivative. All right, let's see, I had a request for another optimization and explanation of how to think through optimization. So let me pull up another homework question. Let's see, is it this one? There we go. All right, so I haven't looked at this one yet. We'll see if I can do it on the fly, but a Norman window has a shape of a semicircle atop a rectangle, so that the diameter of the semicircle is equal to the width of the rectangle. What's the area of the largest possible Norman window with a perimeter of 44 feet? So I'm not going to go all the way through this, but just about all the part before we get to the algebra. So again, the idea is when you're looking at these, this is asking you to find the largest possible, let me draw on this, largest possible window in terms of its area. So what I need to do is write an area function. And then once I've written this area function, which is really the hard part of this question, I want to be able to graph this or take a derivative of this. So I need it to be a function of one variable, but we'll work on that after we get the general structure of the area formula figured out. So Norman window, so we have a rectangular base and a semicircle sitting on top so that the diameter matches the width of the window. So one of these shapes of windows. So in order to have a perimeter of 44 feet, there's some other rules that take place, but that's the perimeter itself isn't something we're trying to maximize or minimize. The perimeter is going to be 44. We'll get to that later. This is a constraint on us, meaning I can't get the largest possible Norman window. I could make it infinity feet wide by infinity feet tall or something like that. No, we can't, because we've got a restriction on the perimeter. But if I wanted to find the area of this, I'd find the area of the rectangle and the area of the semicircle and add them together, right? So area of a rectangle is, I'm just going to write length times width, and the area of a semicircle would be 1/2 pi r squared. But clearly I don't need all those different letters, right? If I label my diagram here, I can see that, since this semicircle matches up with the rectangle, the radius and the length or the width, some of those are the same number, or at least related, right? So let me change colors here. Let's say that I'll make length be the top to bottom measurement and width be the one that matches up with, well, the radius. So right now, this expression isn't too usable for area because it's got 1, 2, 3 different inputs. So if I said, find the derivative of area, like, well, with respect to what? X? Is there some other X and it's an implicit derivative? Are L and W and R 3 separate unrelated variables? If so, then there's nothing that holds this back from being infinitely large. So in terms of this, well, what do I know? I know that these two match up. So the radius is half of the width, or the width is twice the radius. And then the length and the width and something, well, somehow the perimeter can only be 44 feet. And so that's also related to L, W, and R. In terms of, should I use R's or should I use W's? Doesn't matter. You can do it either way. So I'm just going to use R's because that way I can just leave this 1/2 pi r squared alone. And then W would be the same as the diameter, 2r, right? So instead of writing W here, I can write 2r. It would be just as valid to leave this as W and call this 1/2 W quantity squared. That would be just as good. There's many different ways you can do this. So in terms of this now, though, I've still got 2 letters, L and R, and I need to not have 2 letters. They should be related because of this 44 feet thing, right? So the perimeter of this would involve, well, let's see, an L and a 2R and another L that would go around the 3 sides that are flat. And then we have to go around a semicircle. So distance around a circle, 2 pi r, but I've only got half of it, so 1 pi r. So here's the distance, all 4 sides, 3 flat sides and 1 curved edge, I guess, whatever you want to call this, that goes around the perimeter. This is what's supposed to be 44. So this is what's going to allow us to eliminate our other extra variable, because L and R can't be anything that we want them to be. They can only add up in this way to make a total of 44 at most. But since we're trying to maximize, I'm going to just say that they have to equal 44. So I've got 2 L's and 2 plus pi R's, just cleaning this up a little bit. 2 plus pi, oops, and this isn't writing very well, and that's going to be a little bit confusing. Where's my eraser? Two plus pi R's. So I've got 2 L's and 2 plus pi R's that have to equal 44. So I could state either in terms of the other. I could solve this to say L equals something with R, or I could solve this to say R equals something with L, and either one is going to be a little bit messy, but based on the fact that if I want to replace R, I have to do it twice. If I want to replace L, I only have to do it once. I'm going to replace L. So that means I'm going to solve this for L. 2L equals 44 minus 2 plus pi R. I mean, you could write this as minus 2r and minus pi r. That's fine. I'm going to divide by 2 now, so that I have L equals, if I divide by 2, I'm going to have 22 minus 2 plus pi over 2, if I can write that, r. So this expression can be put in place of L. And that way, this expression for area, although ugly, would be area as a function of r, area as a function of one variable. And once we have that format, just using relationships that we knew, like the width versus radius, we knew that from the way we drew the picture maybe. The length versus radius, not so easy, but that's based on this perimeter 44 feet relates all the distances around to one another. And regardless of which letters you used, you'd be able to use this perimeter 44 to eliminate the last extra variable. So in any case, then this lovely expression, instead of L times W, I'm going to have 22 minus 2 plus pi over 2, which you could also reduce to 1, plus pi over 2, all times r. But this is times W, well, which is now 2r, and then plus 1/2 pi r squared. But from there, I have area as a function of one variable, and this, I could use GC to graph this, I could use a graphing calculator to graph this, I could take a derivative and figure out when it's equal to 0, because, thinking about the format of this, I've got negative something or another r squared plus a 1/2 pi r squared. It's going to come out to be negative something r squared plus a 44r. So it's some sort of parabola. I don't know exactly where its vertex is, but there is going to be a maximum to it since it's a downward facing quadratic function, a quadratic function with a negative leading coefficient. This is a little messy to see that, but it will have that. So if I find the one critical value that this should have, it's going to happen at the spot we're looking for. The value of, it would be r, a special value of r that makes the area as large as possible. Now, all this question asks for is what is that largest area? So once you find that r, you can plug it back in and find the area, because this is area as a function of r. If you wanted to find all the dimensions just out of curiosity, you could also do that. This question didn't ask for that. But just make sure when you are doing optimization questions, so that you just don't mess up at the very end, make sure you answer what was asked. Like if it said, what's the radius of the circular part that makes the largest possible Norman window? You put the radius here. It says, what's the area, the largest possible area for a Norman window of this structure? You put the area there, and so forth. All right, that's that. So let's see, have any other questions? So the other thing just that I wanted to do is go over, and this is not a specific question, but just again, review the processes that we've gone through as a part of this class. So this is kind of along the lines of overall class summary. Let me find the keynote I'm looking for. Ooh, not with that. There we go, to share with you something else, maybe. All right, so we looked at this at the tail end of last class, but here we go. So just the relationship between rate of change and accumulation. And we started out the class long ago talking about, suppose I know how fast something is changing, and I want to know how much of it I have. So if I know a rate function, how do I get to an accumulation function? That's a reverse of what we've just been dealing with derivatives. But this is the part that we got to almost before your first test. So we went through a process where we talked about estimating. So here's an exact rate of change function. And then we wanted to estimate, let's see, hold on. Why is this not sharing what I clicked on? Keynote. All right. So looking at the situation where we know an exact rate of change, and what we were able to do at that point in time is use a constant rate of change. Well, this isn't constant, but if I look at small chunks, I can use a constant rate of 3, meaning 300 feet per mile for a little bit, and then maybe 3.2, 4, or 3.5, 3, and so forth, but using different rates each for a little bit, and came up with an estimated accumulation based on that. But that was useful if we need to make estimations or do something manually and we don't have an actual function rule. If we do have a function rule, as opposed to just having a graph, then we can do something else instead. We can get an exact rate of change, an exact accumulation function from an exact rate of change function rule. So even if we just have its name, we just call it R, I can write an expression for that, for the exact open form function that gives exact net change in elevation or exact total change if I knew a starting point. But we talked about this at the tail end of last class. If I have not just a picture and I want to estimate by drawing lines and estimating values visually, if I have a function rule, whether it's known or I'm just using a symbol for it, I can write an integral expression to indicate summing up all the different values of this rate function, each one multiplied by an infinitesimally small amount of time. So this wasn't time in this case, it was distance, but whatever this independent variable is, use each rate for a tiny little bit of the independent variable axis. So this is our MDX sort of expression, like rate times time, or in this case, it's rate per mile times number of miles, but using using each rate for just a tiny little increment along the horizontal axis, but then adding them all up. How many? Well, start at A and go through X. If I gave you a specific value for X, that would give you a stopping point. So this open form with the integral reflects the whole process that we go through of summing up, but in this integral form as opposed to the sigma summation form. This indicates using all of the different values, infinitely many, as opposed to counting up a certain number of intervals of unknown width, but only ever having an approximation because we're actually using a constant rate for a while that's visible along the horizontal axis. So our accumulation is the sum of many bits of individual accumulation. Each one is an MDX, a rate times a little amount of using that rate. So where we went with this after we got to that, and we're going to do some more with this both now and through next week, using this idea of exact accumulation to accomplish something. So supposing that E is the actual elevation as opposed to F, which we said was this net accumulation from A. So net is how much elevation we gain starting at point A, miles from the border or coast, whatever it was, and going through any distance X. So F could be written in terms of this graph of what the actual elevation is at any point, just by subtracting, because the net change in elevation should also be final minus initial. It's this accumulation from one point to another, doing one little piece at a time, should have the same effect as knowing like y final minus y initial, the net change in a known value. And so if I know function E, I should be able to find R or F from that. But if I know R, I should be able to find F, or with a little bit of extra information, function E, this actual overall elevation, from function R. Because I can find F. The only thing that I don't know, this net change, I can find changes between two values, but I can't find any individual values of elevation without being given at least one to start with. And that's the equivalent of kind of the algebra 1 problem. Suppose I want you to write an equation of a line with slope 3. Well, it'd be y equals 3x plus something, but you couldn't say the something unless you have one point on the line. You can't write a full equation of a line knowing only the slope, knowing only the rate of change. You have to have some additional point, some additional piece of information to tie it down, and then you can work from there. Otherwise, all you can ever state is relative to a known point, how much you'd change. So our closed form accumulation function, if I want to write it, I can, but there's always got to be either an element of mystery involved, or I have to be given additional information. So I think we talked about this a little bit also back in February after your first test, but kind of as a break from just doing derivative rules all the time. So this is fundamental theorem of calculus is what this is, but a closed form accumulation function, like f of x equals 3x squared minus x. Suppose that this is f of x. I could find f of a for any a that I wanted to. I should also be able to find r sub f, right? Because that would just indicate the rate of change of this. And this is just a power function with two terms. Well, so power function with sums and differences. So I know the rate of change function. I should know that as of like one day of learning about derivatives, some more simplest ones. So I have this closed form accumulation function here. I can find its rate of change. And so I should be able to then also express from this open form of accumulation what this means. So thinking about what this means, this would be, okay, so I know that this is the rate of change function for that. So this should be the net change in accumulation between x equals 4 and a general x, right? So that would mean this is equivalent to f of x minus f of 4, final minus initial. And since I also know what function f of x is, I can put it in its formula here. I can put f of 4 there, and I can get a closed form expression for this net accumulation from this. So meaning f of x is 3x squared minus f, or 3x squared minus x. F of 4 is 3 times 4 squared minus 4. And so I could, write this. It's a closed form representation of this net accumulation between 4 and x. So net accumulation beyond 4. And I could simplify this, whatever this number is at the end. 16 times 3 is 48. Let's see. So this would be the same as minus 44. 3x squared minus x minus 44. Great. That's the same as this. We should, however, also be able to do something similar, even if you're not given this f of x to start with. Because in certain cases, looking at this rate function, you should be able to tell what accumulation it could refer to. So we'll go both directions, but try the same sort of thing with this sine of 4x. Its derivative, 4 cosine of 4x, just a simple chain rule on a trig function. But see if you can write out a similar expression for the closed form of this net accumulation function. Here's the rate pertaining to this f of x. I want to know what accumulates between 0.1 and a general x. I'll give you a minute or so to think about that, and then we'll go on. All right, so again, here's our accumulation function, f. Here's its derivative, 4 cosine of 4x. So if I want to know accumulation due to this rate between 0.1 and x as independent variable values, accumulating at this rate, you can see I should be able to compute that using this f of x here. This is the rate. This is the overall accumulation. So if I want to relate it to this, I just need final minus initial. F of x minus f of 0.1. Ooh, sorry. I clicked unnecessarily without meaning to. So it'd be f of x minus f of 0.1. So sine of 4x minus sine of 0.4. And that's that. This expression is equal to sine of 4x minus sine of 0.4. Now, if I had a number in here instead of an x, then that would tell me a numerical amount of accumulation, or the numerical difference between two values of f of x, between f of 0.1 and f of something else later. So in any case then, let's take a look at what you saw for a brief moment here. This. So here's a rate function. The rate of change of function g with respect to x is given by 3x squared. Think about what each of these would mean, and since I'm guessing you can figure out an accumulation function that has this rate, think about what function it is that has this rate. I think you can evaluate each of these. So think about the meaning of them and then write down the closed form equivalent using something that you can come up with that has that rate. And there's more than one unsimplified answer, but there's only one simplified answer for each of these, up to like what order you list terms in. All right, so thinking about this, a possible function g would need to be something like, well, let's see, 3x squared, but normally I'd add 1 to go backwards. I'm going to add onto this power here. And let me get rid of this coefficient here because that's the 3. So in other words, in terms of this, once you see it, it's easy to find the derivative. But I say, oh, well, anything like x cubed, this could be the derivative for. Now, there's more than one function that has this exact same derivative. More on that in a minute. But would you agree that this would be okay? Using this as g of x, it would definitely have that derivative. So this is the net accumulation between x equals 1 and any value of x at this rate. At this rate, r sub g, this is of t times dt. But to evaluate this then, I can just do, since this is r sub g of t, I can say, oh, well, then what accumulates is g final, g of x, minus g of 1, which would be x cubed minus 1 cubed. Now, what I said a minute ago, and we'll get back to this, back to those other two questions in a moment. This is not the only possible g of x. Because if I did something like x cubed plus 19, it still has the exact same rate of change function. Constants don't affect the derivative, and that seems like it'd be a problem. but it's not if all I need is net change. If I think about this, this is a rate for either just plain old x cubed plus 19, x cubed minus 97,000. This is a rate of change for all of those. All of those change the same way between x equals 1 and any value of x. They don't have the same y values, but they change the same way. All of these constants do at the end is shift the graph vertically. So although g of x isn't the same and g of 1 isn't the same for this old function I had and my new blue g of x function, if I did it with the blue g of x function instead, I'd have x cubed plus 19 minus 1 cubed plus 19. And you can maybe see that, well, net change-wise, the 19 cancels out. I've got a 19 here and a 19 there after the subtraction sign. So I end up with the same net change, x cubed minus 1. So in answering these net change questions, how much changes between the beginning and the end, constants that don't affect the steepness of a graph, that don't affect its derivative, that don't affect its rate of change, also don't affect net change. They don't affect how much happens between any two boundary points. They only affect what the individual y values are. So x cubed plus 19 obviously isn't the same as just plain x cubed. Or 1 cubed plus 19 isn't the same as 1. But with this plus 19 just added on to both halves of the subtraction problem, both halves of the y final minus y initial, it doesn't change the result. It goes away in the end. So these other two questions down here, it doesn't matter what function I come up with that has this derivative. All I need to do is come up with something, any function that has this as its derivative. So might as well pick the easiest possible one. That's simpler than dealing with extra stuff that could be there, but we don't need it. So on these other questions, if I wanted to know, well, what's the change between -2 and x? Y final, minus y initial. So g of x minus g of -2, which should just be x cubed minus -2 cubed. So minus -8. Or in this case, g of x minus g of pi plus 2. Now this one I'm not going to cube out, but it'd just be x cubed minus pi plus 2 quantity cubed. So in any case, these sorts of questions here, these net accumulation, as long as you remember what they mean, if you can come up with, based on, relatively simple, and this is something we're going to work on some more complex derivatives to undo, finding an antiderivative. So moving from this x cubed or 3x squared to finding this x cubed, it's undoing this process of a derivative or figuring out what sort of thing has this as its derivative. This is typically called finding an antiderivative. Finding this formula whose derivative we know is finding an antiderivative for this 3x squared, for this rate function. So we use the same antiderivative for all three of these, just this x cubed, because it doesn't matter which one we use, we just have to find an antiderivative, any one we want. If you wanted to do x cubed plus pi for every single one, you're welcome to do that. It's just extra work, because each of these only represent net change. I don't need to know individual values of g of x separately for my final answer, only the difference between, the change between two different values of g. So two different values of anything that has the same derivative are going to have the same difference between them, because net change and overall change, like net change and rate of change at a point, those are directly related. All right. Let me go back to, let's see if I can get this to clear. There we go. Net change. So this is our fundamental theorem of calculus. Again, we've talked about this before in several different contexts, but the net change as x changes from A to B can be modeled by two different methods. I can think about, oh, net change of an accumulation F. I can do final minus initial. I can also add up all the changes that happen between. So either using F, the accumulation function, directly and looking at the change between the beginning and the end, final minus initial, or using the rate of change of function F and expressing it this way. So this is expressed in open form. This is the same thing expressed in closed form. And this uses, instead of an A and an X, this is just using A and B. So this is typically used when we're talking about numbers, but it could be either one. These are equal to one another, but I could change those to X's and have it be exactly what we'd written on the last page. This A, you can think of that as like a reset, or just let's start accumulating at point A. So this is talking about a net accumulation beginning at A, so it doesn't take into account whatever happened before independent variable value of A. And so this is, again, the same thing. It subtracts off everything that happened up to point A. So all I've got is what happens in between. But just realize that f of A itself isn't 0 necessarily. It could be, but there's no reason that it has to be 0. All this is talking about is, it's like a final minus initial sort of situation. If this is a number 0, this is a number 0. It still doesn't mean that the value of this initial component, this initial point of the function, has to be 0. It might be, but it doesn't have to be. But this is just net accumulation from A through X. This is the net change between A and X. This one uses the rate function. This uses the accumulation function, and they both give us the same value. They mean the same thing, just computed in two different ways. This one requires that you know the accumulation function, or an accumulation function. This one requires that you know a rate function. All right, so just one quick last thing before we go for today. And I think we talked about this also back in end of February, beginning of March. If you remember, here's a rate of change of our height function, which is a power function. Rate of change of the height with respect to time is t to the 1.3 power. This was our rocket basketball back from, I don't even know when we talked about this guy in January. It was the first time we talked about this actual problem. What we used it for at the time was making an approximate rate function and then estimating accumulation in height. But using this rate function, see if you can write an open form expression for the exact change in height between time 2 and 5. Ooh, sorry about that. Keep hovering over that bar. There we go. So if I want an open form expression for the exact change in height, this open form just means you don't have to write a simple function rule. I can express what needs to happen. And if I want to evaluate it, God, go away. Hold on, I'll wait till this bar goes away. No, maybe it won't. I might have to just turn this off. There we go. So I should be able to evaluate it and then also write an open form and a closed form of this. I'm going to have to get out of presentation mode here, because otherwise that will keep popping up. So what I want is an open form for what happens between time 2 and 5 for the net change in height. Let's see. So the change in the height between t equals 2 and t equals 5. So on that interval. And then evaluate that. And to evaluate it, we need it to not be open form anymore. We need to think about what is a potential antiderivative of this that I could use to evaluate this open form, to express it using the subtraction. So in other words, I need to figure out what's a function for h where I can do h of 5 minus h of 2. But notice that h isn't given, only r sub h. And then the third part was an extra bit. I'll get back to that in a second, but do these two first. Take a couple minutes. And when I say evaluate, don't worry about getting a decimal value. Just write it out in using function notation or using, whatever your antiderivative is. You can write it out that way. This is being really stubborn. All right, so this open form, change in height between time 2 and time 5. Okay, oh, well, that should be the exact rate of change, what occurs between letting time take on all the values between 2 and 5. So I'd have t to the 1.3 power dt, or pick your favorite letter. It doesn't matter if it's t or something else. But this expression here represents using our function rule for rate at all the values between time 2 and time 5, each one for an infinitesimally small amount of time. I should also be able to come up with something whose derivative is that. Now, this is not quite as easy as find an antiderivative for 3x squared, but, and I think we talked about this before, it would need to have one higher power. Now, if I took the derivative of this, it'd be 2.3 times t to the 1.3. So I'll put in something to cancel out that unwanted coefficient. So this here, our height is 1 over 2.3 times t to the 2.3 power. If I took the derivative of this plus any constant I wanted, it would be that. So I'm just going to use the simplest version, not worry about any constant. So I'll use this at 5 and at 2 and subtract. So to kind of simplify up the algebra here, one or lessen the amount of writing, it'd be 1 over 2.3 times 5 to the 2.3 power minus the same thing times 2 to the 2.3 power. So I'll just group it, 5 to the 2.3 minus 2 to the 2.3. Each one would have that same coefficient on it. So here'd be an exact evaluation of that. If you put this into GC and ask it to evaluate versus putting this into GC and asking it to evaluate, you should get the exact same values for both of those. Now, the third question that was asked that I pulled out of because it kept activating that little video play bar on Keynote. The third question is asked that suppose that the ball was launched from a height of 6.5 feet, I believe is what it said, which translated into math is this. So the rocket basketball had an initial height of 6.5 meters, sorry. So suppose this was true. And what we want to find is the actual h of t. So if we have this information here, I can find h of t, the function, using this because I know where it started from. This is like being given the y-intercept in addition to our slope and being asked to write the equation of a line. Now that I have both of those pieces, we can do it. And how that works is kind of the same way, right? So when you had a y-intercept, that's the easiest one to work with in terms of writing equations of lines. You have like y equals mx plus b, plug in a y and x and solve for b. Well, if I want h of 0 to come out to 6.5, and I know that h of t is something like this, 1 over 2.3 times t to the 2.3 power, plus anything I want, you could call it a b, whatever. I know that if I substitute in 0, it's supposed to come out to 6.5. Well, just like linear equations, this one, because it's a power function, this doesn't work all the time, but because 0 to any power is going to be 0, if I were to substitute in 0 for t and 6.5 here, I'll figure out that this number has to be 6.5. So it's only because this is a vertical intercept sort of spot, because it's a starting value, t equals 0, and also because this is a power function. If this had been an exponential function, like 2.3 to the t power, when I sub in 0, this term with the variable does not come out to be 0. There's a lot of different ways that we could have to do work, but this one's an easy one. It's just plus 6.5. Now this has the same rate as we had before, but instead of just being something that has this rate, it fits another qualification that meets the specific qualities that our height function has to have. So this was always drawn, even in your textbook, a little bit higher than that. Like this is just a picture of it launching. So you can imagine, oh, it's not launching off the ground, it's launching from something higher. So if it was 6.5 meters, here's our height function. And if you did h of 5 minus h of 2 using this, it would still come out to be the same exact thing as before, which I don't know what this is as a simplified decimal. It's an ugly number with 2.3 powers. It's not going to be anything nice. But in any case, that is it for today. For before Thursday, make sure, go to office hours, email, post to message boards, whatever it takes to get your questions answered, because your test is on Thursday. You can access it starting at 9 a.m. Arizona time. It is only available through 10:15 a.m. Arizona time. You cannot access it later. You will get kicked out at 10:15. So if you want the full 60 minutes, make sure you start between 9 and 9:15. All right, and also try that Respondus browser beforehand so you make sure you know it works on your computer and you have everything set up. If you have technical difficulty, please contact ASU Tech Support. Zach or I might be able to help, but ASU Tech Support can help more directly. Like you can give them access to control your screen and see the settings on your computer and stuff, so they can make sure that that's all set up properly. All right, study well. I'm going to stick around for office hours. You may leave if you are set. If you want to stick around for questions, I'll unmute people's, let's see if I can find everybody. I'll unmute stuff, but I'm going to stop sharing this and just look at the picture here.
Do you know if we're going to have any questions on the test, like the shadow, the spotlight on the wall with the shadow one?
Hi, guys. Anyone have a question?
Yeah, I got one. I got one. Can you hear me?